Yo, what is up, guys? Welcome back. Another day, another video. Shout out GitHub followers. Today's Pokemon sound of the day is Diglett. So I gotta make the sound of the Pokemon of the day. Let's take a listen, shall we? Diglett, Diglett, Diglett. Get me out. Just get me out. Let's just get a Leetcode of the day going. We got prime subtraction operation. I already saw the Leetcode. Huh? Why am I sound out on everything? That's so weird. I was signed out of some other stuff earlier today as well. I'm getting hacked, dude. Alright. What? What is it? Strictly increasing array. The strictly increasing? Yeah, so they can't be equal to each other. I mean, this is pretty simple. Like, I just start at the first element and I make it as small as I can. Um, mhm. Yeah, but this is tricky because, like, let's say I have a 10, right? A 10, and I can do 7 plus 3. I can subtract 7 and I can subtract 3. So, like, how would I know which one to subtract? Like, I can't. Oh, I guess if I had 10, I can do 5 and 5 as well. Or I can do 5 of these. Or does it just not matter? Okay, let's say I had I don't know, 15. Wait, can I only do it once per number? You can perform the following operation as many times as you want. Pick an index I that you haven't picked before and pick a prime P that is strictly less than nums I. So wouldn't I want a list of primes though? Oops. Think about if we have many primes to subtract. This is a weird problem. But I'm just thinking, like, how the hell would I do it without, like, manually copy pasting all these primes? I don't want to do that. I don't know. Why is my seat so low? Like, I swear I don't be making it that low. It's always so low. This is a weird problem and kind of a stupid problem, and I don't really want to do it. I mean, I guess I'll start, like, I don't even know, like, dude, I don't want to do this problem. I'm just going to watch the Leetcode video, and I don't want to do it. Like, I know how I would brute force it, and it just, even thinking about brute forcing this problem, just like, I don't want to do it. But maybe I'm just missing something, like, super obvious.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, prime subtraction operation. This is an interesting problem.
There is an optimization.
A decent amount of math, but also some conceptual challenges with this problem. I'll be showing two solutions. One is more of a brute force solution, but it actually does pass on.
This is what I was thinking. Binary search to approach the closest prime. But, like, how would I do that without getting all the primes first?
Leetcode, and I would say that honestly a brute force solution, given that this is a medium problem, isn't the worst thing. It very well may pass you in the interview. I will also show you a second, more optimized solution, which maybe for a medium problem, you might need a hint to come up with the solution. So we're given an input array. All of the integers are going to be positive. That's guaranteed. We want to transform this array. Well, we don't actually want to transform it, but we want to know if we can transform it such that it will be sorted in strictly increasing order, not non-decreasing order where like adjacent elements could possibly be equal. That's not allowed. They have to be in increasing order. So is it possible to do that? Well, the rules of the game are this. We can pick any element, and we are allowed only to subtract from that element, and we're only allowed to subtract prime numbers. So knowing that, how can we solve this problem? I'll kind of walk you through my line of thinking. It was this. If we pick an element, first of all, we can pick in any order that we want, but it probably makes sense to go left to right. So that way we can kind of validate, okay, this portion was sorted, this portion is sorted, now this portion is sorted, etc., etc. So we could start from the beginning of the array, trying like a brute force approach. We look at 4, it's already sorted, right? Like the next element is greater than 4, the previous element doesn't exist, so we're good. So, okay, move to the next position. 9, it's greater than 4, but it's not less than 6, so we should subtract from here. There's a prime number, I'll just randomly pick one, 7. We could subtract 7 from 9, then it would become 2. Okay, that's technically less than this, but it's not less than the previous, or it's not greater than the previous value. So now you might think, okay, this seems like a backtracking problem, right? So I have to brute force this. I have to make a decision tree. I might have to go back. But no, that's actually not the case. We can, instead of going back to 2 and seeing, okay, well, is there a prime number I can subtract from 4? Yes, there is. We can subtract 3 from 4, and then it'll be 1. And then this portion of the array is sorted. Instead of having to backtrack and do that, why don't we just be greedy? We just want the array to be sorted. We don't necessarily know what's coming.
But you need a list of primes
up ahead. We really don't. I mean, there could be some
that's
really
stupid.
small
if I have to do that in
values
a problem,
here.
if I have to get a list
For example,
of primes
like this could have been
a
a 3. So what kind of greedy approach should we take? Knowing that we can't predict the future, we should try to, every time we look at an element, not only should we try to make it such that it's sorted, like it's less than the next element and greater than the previous, but we should also try to minimize each element. How are we going to minimize each element? Well, we can only subtract prime numbers, so thus we will choose the largest prime that we can subtract from each element as we go. This way we don't need to do any backtracking or anything like that. By the way, one thing I didn't mention earlier is that yes, we're allowed to subtract primes from any of these given numbers, but we also want every value to remain positive, so we can subtract like the largest possible prime. But if a number itself is prime, like for example, if we had 7, we are not allowed to subtract 7. The largest prime we would be able to subtract is 7 minus 1, which is not a prime number. Just keep that in mind. So knowing all that, this is how we can solve the problem. Okay, for the first number, 4, what's the largest prime we could subtract from 4? Well, we can brute force just getting every number that's less than 4. So 1, 2, 3. These are all the numbers less than 4. In other words, this is the upper bound of all the numbers less than 4. And so among all of these, we want to figure out which one of them is the largest prime. So we can kind of go through these in reverse order. Check, is this a prime? If it is, then we can stop. We found the largest prime. If it's not the largest prime, we will go left and try to see if there are any primes here. Now, in this case, 3 does happen to be prime. So 3 is the number that we would subtract from 4. Now, how would you determine that a number is prime? Well, the brute force way to do it would be like this. A number n is considered prime as long as there doesn't exist a factor or denominator that can divide it such that like the remainder will be 0. So does there exist an f? If it does, then this is not prime. And if there does not exist an f, then this guy is prime. How do we check that? Like this. Just get every factor from 2 all the way up until this number. But actually, if you want, you can stop early going all the way up until the square root of that number, because we don't need to check any factors beyond the square root.
Yeah.
And if you want the intuition of why that is, consider something like 49, where the square root of it is 7. So we would only need to check up until 7, because anything else, like for example, even if there was a factor over here, it must be multiplied by a number that's less than the square root. And if this is a factor, then we would have already found the factor here, and that's why we can stop at 7. So knowing all of that, now we can solve the problem. Assuming we have a way to find the largest prime, we can do this. Take 3, now subtract it from 4. We're good. We'll have 1 here, and now we'll move to the next position. We want to know what the previous element was, because we do want to make sure that this is greater than the previous element. So now, from here,
let's implement this brute force. Honestly, it's not as bad after he kind of described what I thought he was going to do. I mean, this is not a medium then, but okay. Here, let's make a function def helper n for I in range 2 to I need a floor. I need to floor it. Oh, why'd I go to 6? Oh, that's +1. 7. Okay. Should I go from it backwards? I should go backwards. Int of sqrt of n -1. Except this needs to be 1, right? Because it needs to stop at 2. Yeah, okay. If modulo I is that's the largest prime, but that prime might be too big. Right? So I would want a list of them. Um, I guess it's not. It'd be R. It'd be like this. 2668. That's not right. Right. Wait. This doesn't even make sense. Wait, what? Why is it 3? Why is 3 the only thing in here? Wait, am I calculating these primes wrong? Well, I'm an idiot. Yeah, I'm an idiot. Wait, I'm stupid. What am I doing? Wait, I'm like literally a rock person. But I'm getting the factors. Wait a minute. What am I doing in this code here? Okay, hold on. This function is supposed to help me get all the primes up to this number. Wait, hold on. Dude, I'm actually having like a brain like explosion right now. I'm so like my brain just doesn't want to work right now. How do you calculate primes again? It's just break. It's break. 7532. 532. That's right. Oh, and then we just break here. Or maybe we don't break, but we continue. Is that what we do? No. No, we break because of this right here. One, two, three, five. Okay. For I in range. 1, 2. If nums at spot I minus 1 is greater or equal to nums at spot I, return false. Other than that, return true. I mean, I'm pretty sure this like passes the test, but like this is super slow. Or it just TLEs from the get, which would be not cool. Because this is the thing taking up all the time. Yeah. I'm sure not to do these recalculations. No, I really should just do like R equals helper max of nums. Okay. And then return, and then print R. I need to use this test case. Is there really a number that's 1,000 in here? Or that's larger than 991? $995. Okay. So that's nice. We got that. And then now we need to okay, what if without doing the binary search, I just brute force it? Just out of curiosity. What happens? I don't want to brute force just yet. For num minus Yep. Hmm. 997 is a... Huh? $997 is right here. If gnome 998 minus 997, how did this not activate? This like literally should work though. $997. Uh-huh. Not entirely sure why this is not working. 997. No way. I mean, it's there. Oh, I need a break from it. Oh my god, I need a break from it. I need a break from the ads. Yeah, bro, what was I thinking? That's obvious. Come on now. Okay, binary search definitely makes this go faster. I think if I, because this array is auto sorted, right? When I do this, so I binary search through, but I don't want to do that. So I don't want to do that. That sounds like a lot of work. So let's just take a look at what he says.
We want to do the same thing. Just remove the largest possible prime. And in this case, that happens to be 7. So if we subtract 7 from 9, we will get 2. And that is greater than the previous element. But it could have been possible that maybe we got a number that was less than the previous element. An easy way to avoid that is, rather than checking all prime numbers from like 1 through 8, remember we skipped the 9 because we don't want to set this to 0. Rather than checking if these are prime numbers, we know that if 8 happened to be a prime number, we would not want to subtract it from 9, because if we did, we would end up with 1 here. We want the array to be in increasing order. This is not the case. So what we actually do is we take the current element, 9, subtract it from the previous element, 9 minus 1. That gives us 8. So now I'm going to check all numbers less than 8, so 1 through 7, and check if any of those are prime. So you can kind of think of it as like this being the upper bound of numbers that we need to check. And the upper bound is not inclusive. So basically we check everything less than that. And I know I said 1 through 7, but I actually meant 2 through 7, because we already know that 1 by definition is not a prime number. Anyways, now let's code it up. I'll just leave these comments in case they're helpful, but we can get started now. I'm going to define a helper function is prime so that we can determine if a given number is prime, because remember, we are going to kind of brute force this. So given n, is it prime? For now, I'm just going to assume that it works, and we're going to use it to solve the rest of the problem. And then we'll come back and fill it in. I want to go for n in nums, every number. I want to calculate that upper bound I was talking about. So I want to take n and subtract from it the previous numbers. So I'm just going to have a variable for the previous number. Initially, we can just set it to a neutral value like 0. We already know that 0 is less than every number in the input, because every number is going to be positive. And we also know that since it's a neutral value like 0, it's not actually going to change the value n. And this is the upper bound. But remember, the upper bound is not inclusive. So this is technically not the largest number that we could subtract from n. This is non-inclusive. I'll just make a comment for that. Non-inclusive. The largest prime we could subtract is technically this, minus 1. So keep that in mind. But when it comes to Python, it won't be a problem. You'll see why. So I want to figure out what is the largest prime. Again, I'm just going to initialize it to a neutral value like 0, basically saying we have not found a prime number yet. So now I'm going to check every number. For I, is I a prime number? I'm going to go from 2 up until the upper bound. In Python, this second parameter is not inclusive. So this loop is going to check everything from 2 up until upper bound minus 1. We skip 1 because 1 is not prime. And also, for this, we could go from left
solution
to right,
is going to be the
but
binary
it would probably
search.
be better to go from right to left because we're just trying to find the largest one. If we find one, we can just break out of this loop. So I'm actually going to take this and reverse it. And then in here, I'm going to call is prime on I. If it is prime, I'm going to set largest prime equal to that number. And then I'm going to immediately break out of it. As soon as we find a single prime number, we break because we're checking from largest to smallest. Now, after that is said and done, this is the largest prime we were able to make. We should check that n minus the largest prime, because remember, that's the whole point of finding the largest prime, to subtract it from n, if this is greater than the previous number. Well, if it's greater, that's good. But if it's not greater, if it's less than it or equal to the previous number, that's bad. We return false because that means it's impossible to make the array in ascending order. And so then down here, if we didn't execute this return statement, we can then actually update the previous number, set it to be n minus the largest p, so that it can be updated for the next iteration. And this is pretty much it. If we never return false here, then we will assume that we did indeed put it into sorted ascending order. And the only thing left for us to do is to fill in this little helper. Normally with an isPrime function, you'd want to add like an if statement to check if the number is less than 2, or even if it's negative, then you would want to return false. We say that that would not be a prime number. But the reason we actually don't need to add this time is because we already start at 2 anyway. We'll never go below 2 when we pass like I in as a parameter. So we don't need to do that. So I'll just not put it there. Then we want to check every factor of n from 2 up until the square root of it. So for f in range from 2 up until the square root of n, which could be a decimal, so we want to round it, and this will round it down. Converting it into an integer will round it down if it's a decimal. And since this is non-inclusive in Python, we will just add like a +1 here, because we do want to try the square root.
So I was
we
kind
know
of on
that's
the
a factor of n.
It's
we
just the
want to
math is
determine
tricky
if
for
that's
me.
a
I'm
prime
not
number.
very
So
good at math.
we can
so I
determine
gotta work on
if
that
n is a
probably.
prime number, if it can be modded by the factor that we are choosing. And if that remainder equals 0, then n has a factor of f, so it's not a prime number. We return false. Otherwise, if we never find a factor, we can return true. That means it is a prime number. So this is
Oh no, he did do what I did,
code.
except he did it like a dumbass. Okay, one sec, be right back. We're back.
It works, and it's actually relatively efficient. If
I think his is faster because
we analyze the time complexity, we can clearly see this loop is going to iterate n times, so big O of n, and the inner loop here is going to iterate this many times the upper bound. In the worst case, what could the upper bound be? Well, proportional to n, an element inside of the array. So what's the max number inside of that array? That's kind of what this is proportional to. So we'll call that m. So n times m. Now inside of this loop as well, we have a function call. And unfortunately, that function call actually has a loop inside of it as well. But this one isn't so bad. What we're passing into it is a number. In the worst case, again, it could be the maximum number. But when we iterate, we're not iterating m times, we're iterating the square root of that number. So here we'll do times square root of m. So this is the overall time complexity.
Okay.
So it depends a lot on the max number. Square root usually isn't super inefficient. This might be inefficient though. So in terms of optimizing this solution, I'm actually going to show it to you just in this code because I honestly think it's easier to explain in terms of code. Most of this code is pretty straightforward. I think one of the big bottlenecks we can see here is we're calling isPrime on a bunch of numbers. For example, this sequence from 2 up until upper bound. Maybe one of the times we do that, it'll be something like this, from 2 all the way to 7. And maybe the next time we do it, it'll be 2 all the way to 4.
Yeah, you're
and maybe
repeating
the
the
next
work.
time,
And then, dude, I'm telling you, it's the
way
binary
to
search,
9.
bro. You want to
For
do this
each
immediately and then binary search through it. Like I did, except I did linear search because I'm lazy as fuck. So
number in this range, we're going to determine if it's
okay,
prime. We're
when
going
you
to
have
ask.
to do the binary search, you have to get the number. The number's not going to be in there, and then you have to take all the indices, like minus, like screw that, bro. Oops.
Is 2 a prime
Watch me
number?
just be wrong, though.
Is 3 a prime number? Is 4 a prime number? And clearly, it's repeated work. We're doing it multiple times. So why don't we just pre-compute those prime numbers,
Yep.
and then we won't have to make this function call? Well, how do you pre-compute it? How do you know how many numbers to pre-compute in the first place? Well, without using like the constraints of this problem, which is kind of a shortcut, we can clearly see that whichever like end value among all of these is going to be maximal is the one that we would choose.
Yep.
This is like the upper bound. And what could it possibly be as the max value? Well, n is a number in the nums array, so the max value in the nums array minus 0, because that's like
It
the
is
smallest that
binary.
this
I
can
was
be.
right, bro.
So we only need to compute prime numbers up until then, up until the upper bound. And really, we could probably do upper bound minus 1. So that's exactly what I'm
I
going
ain't
to
doing
do.
all that.
I'm going to do some pre-work up above here. Rather than calling this here, I'm going to create an array, which
I
I'm going to
literally
call
did this, except I
primes.
just did
We
it binary
already
search
know
through
that
it.
0 and 1 are not prime, so I'm going to have an array and fill the first 2 values with false. What this array represents, primes of I, is going to be true if I is equal to a prime number. So we're going to
Wait.
go through every number for I in range 2 up until the max in the nums array. This is technically not going to include the max number because we know that in reality, the upper bound is going to be the max number minus 1. Like that's
What is
the
this guy
highest it
cooking
could
right now?
actually be. So that's why it's done this way. You could do a +1 here. It's not going to hurt. But anyways, we want to know, is this number prime? Let's do the function call. Let's check if is prime I. And if it is, let's set primes of I to be true, and we actually have to append in this case. So I will do that, append this to true. Otherwise, append it to false. And this works. We did the pre-computation, so now we're going to make an intelligent decision down here. Instead of making a function call, which we know
Wait, I guess that's kind of okay. That means I don't have to do binary
is
search
square
then.
root of n. We're going to do a array lookup, which is constant time. So rather than is this prime, let's use the array primes at index I, and then the rest of the code stays the exact same. So I'll just quickly
Wait,
run
that's
this
low-key genius though. No binary search needed.
to prove that it works.
Well, I actually really
and
like
you can
that.
see that it does. I believe the runtime actually might be less than the other one. But anyways, in terms of big O runtime, this is more efficient. I'll quickly analyze it. Analyzing this part here, we can see we're still looping n times in the outer loop. So we're going to get n.
Yeah, but it's
and
only
the
times
inner
m.
loop, we still have that inner loop, which is going
times
to
m.
iterate m times. So n times m. And plus for the work that we did up above. Here we're iterating m times the max number, and then inside of there we're calling is prime. We know that's square root of m, so this part is m times square root of m. So it is an improvement. You can see that the largest term up above
Oh, yeah, I guess.
is going to be larger than either of the terms down here, given the fact that like all of these are going to be integers and not like decimals that are less than 1. Now you might think you're done, but actually there is a way to do it even better. We can get rid of this loop in here as well. And that's actually going to require being a tiny bit clever. We can actually make this array a little bit better, because what we really want to know is with this upper bound, what is the largest possible prime? Well, in reality, we're doing upper bound -1 because we know in Python, these loops, this is not inclusive.
Right, because you're going over a lot of falses, right? It's like false, 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 false. That's why it sucks balls. That's why you want binary search.
But
All right, never mind.
anyways,
You can't escape
what
it.
I'm trying to say is I want to change the definition of this array up above. I want primes of I to be equal to the largest prime that is less than or equal to I. This represents the largest prime less than or equal to I. Because if I had an array like this, if I had one, this is what I could do. I could just say down here, don't give me a loop. I don't want that. Largest P, I already know what that is. I pre-computed it. For this particular upper bound, it'll be this, upper bound minus 1. Because again, that upper bound was non-inclusive. That's how we defined it originally. So now the only thing is, how do we build an array that satisfies this definition? Well, let's say I was trying to determine, is a 7 prime? Like I is equal to 7. So let's just do that. I equals 7. Is 7 prime? Because if 7 is prime, then obviously that's the largest prime that's less than or equal to I. Like that's the largest it could possibly be. So that's what we should check first. And if it's not, well then the largest prime less than or equal to 7 is going to be the same as the largest prime less than or equal to 6. Because remember, this isn't prime factorization. We're not checking if that prime number is a factor of this. We're just checking what's the largest prime number that is less than or equal to this. And if 7 is not prime, then get the largest prime less than or equal to 6. So this is how we would compute it. For the first two positions, I'm going to put 0 and 0 because we know that 0 and 1 technically don't have like prime numbers that are less than them. But then we will loop similar to how I've done it below, actually, from 2 up until the max number. And we'll check if that number is prime, then append to this array the number itself. It's the largest number. That's prime, less than or equal to that. Otherwise, we will append to it the previous prime at I minus 1. Now, the base case is really 2 because 2 is a prime number. So we're going to have 2 appended here. And then we'll just kind of keep going. We'll say, okay, now give me 3. Okay, now is 4 a prime number? Nope. So the largest number that's less than or equal to 4, that's prime, is actually the previous number, 3. Then we'll check, is 5 a prime number? Yes, it is. 5's a prime number. 6 is not, so we give it a 5. Is 7 a prime number? Yep. So that's just kind of the dry run. But this is pretty much it. That's the whole code. And this further time complexity, you can see that the pre-work we're doing up above is still technically m times the square root of m, but the loop down here is just n. So for the new time complexity we have is this, getting rid of that and this. This is the final time complexity of the solution I'm showing you right now. And it's definitely an improvement over the previous, first one that we had. Let's give this a run. You can see that it works. I guess the runtime on Leetcode was worse than the others, but I can confidently say that at least big O runtime, this is more efficient. If you found this video helpful, definitely consider checking out neetcode.io. It's got some really incredible free resources. You can see that it definitely took a lot of time to create this stuff, and I honestly think it'll be valuable for you.
Be right back. All right, I'm back. So we got to work on, I think we're almost done with the music player project, which is so exciting. Let me tell you how exciting it is. Package? Oh, thank you. Thanks so much. Oh, roommate just gave me a package. Okay. Am I tripping? Why? Is it? Oh yeah, that would make sense. Wait. Just give me a sec, guys. I don't know what's going on. Oh, here we are. No song selected. I mean, how's that? Okay. Yeah, so no, that actually looks good, I think. So now I just need to I mean, it's like done. I just need to finish it again. My playback bar. Maybe this shouldn't be here. This should be it's not even that. It's not terrible. Not the best. Okay. Instead of I want this to be vertical. It's flipped. Of course it is. Okay, man, what happened to the slider bar? Why does the slider bar look like that, y'all? Man, I just know a lot of these controls are doing absolutely nothing. That's the thing with AI and like styling stuff, it just becomes a nightmare. They low-key be getting lost. Oh, wow. This is it, guys. This is the complete product. All right, so let's just do a quick showcase of the product here. So what kind of features we got? What kind of dope features we got? So I'm not gonna lie, guys. This is flipped. I don't want to fix it. This is 0 volume. This is max volume. Okay. I don't care. Okay. But here's how it is, right? So this song player has a couple features. What kind of features has it got? First, it got a song search feature. So we have a songs folder. Probably should have this pulled up before I started explaining it, huh? So we have the songs folder, right? I just got 3 like default songs in it, whatever. It's using a try, so you can like look up things, right? And like if you have like 100+ songs in here, it's easy to like look them up. Right, then it quickly, Night Detective, for example, pretty easy. And then you can do the plus sign and add it to a playlist. As you see, this is not styled. You cannot add anything to this main playlist because this playlist consists of your song folder. Okay, you can only add things to the queue, which is this thing right here. But I digress. So let's just go to like the second playlist. I have just the second playlist just automatically configured. I got all these songs. Let's say I want to add this one. I really like this one. I can add it. Bang, add it. It does not support, like I can't move things around. Not supported. But let's say I click on a song in the second playlist. I want to click on this song. What it does is it automatically plays the song here and then queues all the songs after it, right? Because it's like a playlist. You can like right click on these songs and add song to queue and all this. You can go to a different playlist. I think. I hope this is supported functionality. Yeah. See, you cannot queue playlists. You guys cannot hear the song because I have it muted, so I don't get copyright striked. Apparently, these songs are copyright. We got the little playback bar going. Little volume, next, previous, pause, play, do whatever you want. It works. No bugs, as they say. I think it looks really good, honestly. I think this UI looks pretty chill. You can add a playlist, like playlist 2. You can like add all these to playlist 2. You can see the UI is a little bit like, what is this box? But I don't care. You can delete playlist. I guess it doesn't give you a confirmation. You just straight delete it. You cannot delete the main playlist, obviously. Should delete this one. Interestingly enough, these songs stay in the queue. And that's a bug right there. Yeah. Man. How much time I got left? Okay, I'm going to work on fixing that bug, and that'll probably be the last thing I do. So the bug right now is, guys, that when I delete Man, this is just. So I'm gonna add all these songs. If I play this, and then I delete. Oh no, there is a confirmation. And I play the next song. Wait, what? Huh? I have no idea how I made the bug. I don't care. The bug's not here. It's not here. Probably just like did something too fast or something. What happens if I fill this queue? Like, what happens if it goes past? Oh, the Java effects is like kind of buggy. Does it just keep going infinitely? Yeah, it does. All right, well, I think that's it. Now, guys, I gotta look at what the next project is. I think it's something a little bit. It's not gonna take as long. It's like something. I think it's a Sudoku solver. I gotta implement the algorithm to solve the Sudoku puzzles. Let's take a look. Yeah, implement an algorithm to solve Sudoku puzzles. C++. Okay. No more Java for a little bit. Okay. Maybe we'll just watch like a video on some Sudoku solvers or something. I don't know. Sudoku solver algorithm. Oh, comment. Are you doing this music player on your own, not following any tutorial? Backtracking inside code. Python Sudoku solver. This is a good channel. Let's watch this. Okay. Oh. Oh boy. That's exciting. Mm-hmm. Mm. Mm-hmm. I don't know. gotta backtrack. You gotta pop. Yeah. Oh, I had the audio muted this whole time. And for the Leetcode video. That is brutal.
Empty space, right?
At which point you finished.
And we're finished. So all we have to do, we are finished. We just have to print. Okay. So now what happens after we print, we return, which would mean we pretend we have failed, right? And we look for the next solution, which is actually quite nice. It means we're going to find all the solutions. But I want us to first display the solution before we go on. So there's a little trick here. I say input, and then I say something like more. So there's not really a choice. So meaning I stop displaying this. And then if you press return, you get more solutions. Okay? So let's see what happens. It's called solve. That's quite exciting, right? Ah, that's the solution. All the empty squares are filled. It was very quick, right? Mm-hmm. So we can now say more, and what's going to happen after we say more? It terminates. What does it mean? It means there aren't any other solutions. Okay? Which is a feature of most good Sudoku puzzles, that there is only one solution. But it's actually interesting to see what happens if we remove some numbers. Let's just do this. Let's just copy this grid. And I'm going to remove these two numbers down here. Okay, so what happens? So here we find a different solution, right? Here is the 1 down there, which we couldn't put there, was a 7 already. And if you now press return, we get our original solution, and that's it. So in this case, we get exactly 2 solutions. If you start to remove numbers, then you give more freedom, and that would not be a good Sudoku puzzle. This algorithm here, I mean, it's just an example, as I said, for this general approach of using backtracking. You have a partial solution, you try to extend it. If you arrive at the solution, fine. Otherwise, you try to extend it, call yourself recursively, and if you are getting in a dead end, you just return, and then higher up, you try different solutions. You undo, you backtrack. It's like if you're in a maze, you know, you go and you remember, oh, I was there, I made a choice, there I made a choice, and now I'm in the back end, I go back to my previous choice and try the other solution. Right? That's exactly what we're doing here. We're not simulating how a human would solve this problem, right? It would be possible to do this, using all these constraints to find possible solutions. To program this is actually quite complicated. So instead we do, this program is really stupid. It basically systematically tries all possible solutions via backtracking. But if you get away with this, if you get away with this very, very simple algorithm, very short certainly, it's a bit, I mean, there's a bit the point you have to get your head around this recursion, yeah. Once you understand this, it's really very, very...
I mean, the backtracking, this is just like classic Leetcode problem. Like, this is like... But it's just tricky, because, like, I swear, like, this... Oh, if it's not possible, you eventually return here, and then you backtrack. Oh, no, this makes sense.
Simple. The same idea works for lots of problems, in particular for puzzles. And here's one puzzle which I find really quite tricky. It's called Klotsky. And I don't have this game, but you can always move one of these blocks at a time.
That's cool, that's cool. Let's look up Sudoku solving algorithms. How many are there? Are there like multiple? I'm probably just gonna read this, and that's gonna be it for me today, because I don't want to start it. Probably start it tomorrow. Depends. I just have a really tough week today, so. All right. Okay, yep, I understand what Sudoku is. Right, backtrack, that makes sense. It'd be cool to make a visualizer. It'd be cool to just make this. What the fuck? Yeah, I don't know what the hell this guy's talking about. Alright, I'll be watching this video and then the video's done.
Do you think it is possible to solve the traveling salesman problem, a Sudoku puzzle, and a Rubik's Cube by simply making random guesses as to what the solution is. And here I'm not talking about a brute force approach way, where you try everything until you find the solution. I'm talking about purely guessing what the solution is. Well, not only is it possible, but by the end of the video, you will know exactly how to use simulated annealing and what simulated annealing is, which is the technique
3
that
blue,
we're going
1
to use to
brown.
solve Sudoku. You'll know how to solve
Fucking
Sudoku step
editing.
by step, and I'll provide the code
There it
that I
is.
wrote as to how I solved it, and you will have all the knowledge required to solve the traveling salesman problem and the Rubik's Cube yourself. Now, let's get into the video. So before starting and solving Sudoku by using simulated annealing, let's first start by understanding the basics of simulated annealing. This is an optimization algorithm, which means that it can be used to find the minimum of a given function. The way that it does that is by first choosing a random state and evaluating the cost of the function at this certain state. And then it chooses a new one and it accepts this new state with a probability that's given below with the formula. And in this formula, delta is the cost of the second state minus the cost of the first state. So if the second state has a lower cost than the first one, then the probability of this state being accepted is almost always 1. And if it's not, which means that if this is a state where the cost is higher than the first one, then this is either accepted or it's not. And this depends on the temperature of the function. And as the time passes by and we try more states, the temperature will lower in simulated annealing, which means that the algorithm gets greedier and greedier as time passes by, and it only accepts states which actually make the whole system better. So let's go ahead and look at a simple example. So we first start by choosing point x1 and then point x2. As you can see from the picture, point x2 is at a lower point than point x1, so this new state is accepted. Then we start by choosing point x3 and we compare it to point x2. And point x3 is actually a little bit higher than point x2, but we still choose to accept it because the temperature of the whole system is still pretty high. And we repeat this method over and over again until a minimum is reached. And this is how simulated annealing works, and we'll use these same concepts to solve Sudoku. Now let's see how we do that.
I don't really get it at all.
The approach that we will follow to solve Sudoku is the same approach that we followed to find the minimum cost of a very simple function. We'll first start by generating random states for this Sudoku and see how we do that. If you look at the picture in the right, there are numbers that are green and white. The green numbers are fixed values that are given when we are trying to solve a Sudoku, and we cannot move those. And the white ones are random numbers that I put in there and that we can move around. The way that I fill these random numbers is by putting unique numbers in the 3x3 squares, which means that we'll have duplicates only among the columns and the rows.
Okay.
And when it comes to generating a new state, I will first choose a random 3x3 square, and within this 3x3 square, I will choose 2 random values that are non-fixed and flip them. And this will give us a new state of the Sudoku.
Them? Oh.
Are non-fixed
Okay.
and flip them.
That makes sense.
And this will give us a new state of the Sudoku. But how will we know if this state is better than the other one? Well, we'll have a cost function, and this cost function will calculate the sum of the duplicates along the rows and the columns of this Sudoku. And at this state...
So what, there's 2 duplicates in something? So there's one duplicate, and then where's the second one? Oh, 7 and 7. There's only one duplicate in this row. 4 and 4. So like there's 2 duplicates here on this column, 3 here, right? 1, 2. One, 2. I don't know. I'm counting on this. Like, I just really got to make sure it works. 3. There's a 3. There's 9, 8, and 1 in here are all dupes.
The total cost is 38.
What if you have the same one 3 times? Is that 2 dupes?
We're trying to bring this cost down to 0, which means that there are no duplicates along the rows or the columns. And that means that the Sudoku is solved. So those are the 2 main steps. Now for the third one, we have to choose a starting temperature to solve the Sudoku. And the way that we do that is by calculating the standard deviation of the cost for 200 starting states. And whatever the standard deviation turns out to be, that will be our starting temperature. And I chose to use this method based on a paper written by Dr. Lewis on solving Sudoku with simulated annealing, and I'll put a link down in the description below. The next thing is calculating the number of states or iterations per each temperature, and that will be the number of free entries squared. So let's say for a given temperature, we'll try 100 or so states to find whichever one is the best one. And this is called homogeneous simulated annealing. And last but not least is choosing a cooling rate. And I personally chose a cooling rate of 0.99. And the reason why I chose that is because it gave good results by trying it experimentally. If you could go with something like 0.95, the algorithm would be faster, but it is not guaranteed to find a solution. So this is how you solve the Sudoku. You can follow a very similar approach to solve the traveling salesman problem or to solve a Rubik's Cube. If any of you would like to do that, I'd love to see the code for it. And I'll put the code that I did for the Sudoku down in the description below. And before we end the video, let's first look at this code in action. So I won't go through the code here, but we'll just see the code running. You can find the code in GitHub and try running it yourself. I have a starting Sudoku here where zeros are the empty entries and every other number is fixed number that is given in the Sudoku. So let's see it running. So here you can see the number of errors dropping and it drops down to 0, and then we have a solved Sudoku. It was as simple as that, just by using random guesses and using luck, which fits very well with the channel. So if you made it this far into the video, please...
Okay. Alright. That's going to be it for me today. Peace.